How's it going? Hope you're doing alright. Do you have any questions before we get started or continue? What are y'all covering right now in the other class? Linear programming. Okay. Hopefully that stuff that we did working with finding equations of lines and graphing lines is coming in helpful there. Well, that's the whole point of this course, is to kind of prepare you all for the other class as we go forward, as we move forward every week. Okay. Well, today we'll continue our discussion of section 1.7 on factoring. Or no, I think we're still in 1.3. Sorry. We'll eventually get to 1.7. Maybe not today, but maybe today. Let's see how it goes. Last time we looked at factoring greatest common factors, factoring quadratic trinomials of both types, where either we have a number 1 in front of the x squared or we don't. Now I think we only did 2 of the examples where we have something besides 1 in front of the x squared. So I would like to do one more of those before we move forward. Let's see, this will be number 34 on page 24. And we have 15 u squared plus 4u minus 4 Okay. Now again, we have A and C. Multiply those together as negative 60. So we want two numbers that multiply to negative 60 and add to B, which is positive 4. So multiply these together. We want two numbers to multiply negative 60 and add up to positive 4 in the middle. And again, there's different ways that this could happen, but only one way in which the numbers also add up to positive 4. Okay, so we can start looking at the different combinations if we want. You could go through this mentally if you prefer. Let's see, 5 times 12. And 6 times 10. So which of those combinations, we have 12 different combinations possible, because we have negative 60, and that's really what complicates it, is that having a negative number basically doubles the number of possibilities that we have. But again, we have these 12 combinations. Only one of those combinations is going to add up to a positive 4. And we can see that that will be negative 6 and 10. Good. All right. Now, you don't have to write all this stuff down. It's one way we can proceed if we're just not sure of what we're looking at. Excuse me. But, I mean, it's one way that we can just compare our different options and see which one actually adds up to 4 like we needed to. It does require that we know all the different factors of the numbers that we're working with, but as you can see here, I kind of went in order 1, 2, 3, 4, 5, 6, and I did one negative and the other positive, and then switched. So that's kind of a nice way to go. And then once these are close enough together, there aren't any more between them, then we know we can stop. Alright. Now, when we have, I guess that's a u, sorry. When we have this 15 in front of the u squared, again, we don't directly factor this and split. Instead, we split up the 4u that's in the middle according to what's given here. So we took that 4u and turned it into a negative 6u plus 10u. Now, from that point, this is again a u, I'm sorry about that. At this point, we use a process called factoring by grouping, which we outlined last time, in which we group the first two numbers together, or first two terms together, and we group the second two terms together, such as this. Now we need to find the greatest common factor for each set of these parentheses. So what's our GCF for 15u squared minus 6u? When we look at the 15 and the 6, what number can we take out of both of those? And then u squared and u, is there a u that we can take out? 3. Definitely take out a 3 from both of those numbers. What about the variables? A u? And so we'll take 15u squared divided by the 3u that we're factoring out. 6u divided by the 3u that we're factoring out. Okay. What about our second set of parentheses, 10u and a 4? Is there any number we can factor out of those two? That'll be a 2. Good. And we can't take any u's out because u is only part of one of the two terms. Here we have at least u to the first part of both terms. That's why we can take out a u there. Okay. And again, that 2 is our greatest common factor. So, simplifying, we know 15 divided by 3 will give us a 5. And then u squared, if we divide by u to the first, remember we subtract the exponent, so 2 minus 1 will give us u to the 1, or just plain u. 6u divided by 3u. 6 divided by 3 is 2, and u divided by u basically cancels because they're identical, so we can stop there. Just say 5u minus 2. Now after we factor out the 2 from this set of parentheses, 10u divided by 2 will leave 5u. 4 divided by 2 is 2. And now we notice that both of these have 5u minus 2 in parentheses. And so what we're going to do is, because both of these terms have a 5u minus 2 in parentheses, we'll factor out 5u minus 2. And then the question is, what is the other factor then? So these are in common, so we factored it out, and that leaves the 3u and the plus 2. Now, this is a common occurrence here. What happens is that this common term in the parentheses is one of our factors, and then the GCFs that we factored out, we put those together and make that our other factor. That might be a better way of explaining it than what I had said previously, although I might have said something similar, but realistically, it's the greatest common factors that are being put together right here that we had previously factored out. Okay. And that's a little tricky to be able to recognize that, but that is what ends up happening here. And that gives us our completed factorization. I left out the parentheses, sorry. Okay. All right. Now, there's another way I've seen students do that, where they make like a box with different parts. Don't necessarily remember how to recreate that. But I know some people prefer that, from what I've seen in their work that they've done from other classes. And the idea is that, you know, we have 15. I'm just going to change it to x because I want to write x every time I see it. 15 minus 4 or plus 4x, 15x squared plus 4x minus 4. Okay, the way that it works is, let's see, we have to (15x squared) and minus 4. We have to figure out a way to split those up. We know 15x, I might have written those in the wrong way, but you know, 15x squared is 3x and 5x, and I should write the minus 4 down here. Minus 4, we could do 2 times negative 2, but we have to come up with a positive 4x somehow. So we need one number times 5x and another number times 3x. And again, we're not guaranteed that's the correct factorization, but you know, we would choose in this case a positive 2 and a negative 2. 5x times 2 gives us 10x. 3x times negative 2 is negative 6x, and that adds up to 4x, which meets what's in the middle. And then we pair up our binomials vertically and horizontally, so we end up with 5x minus 2 times 3x plus 2. So there's a way to do that, and I don't know if I'm showing you the correct way or I'm showing you one way, but it's really based on guessing and checking. You know, which combination, you know, we know that we have to have 15x squared minus 4, but which combination is going to add up to the 4x that we have in the middle. So I don't know if that is appealing to anyone. Maybe I haven't explained it properly, but it is another way that we could work that problem, just guessing and checking. I like having a concrete method that works, although if you can figure this out, it certainly is much faster than what we were doing. So there are some pros and cons to this. So just to look at a different example, 36. We have 12y squared plus 7y minus 10. Now 12y squared we think of the different ways we could factor that. Probably 4y and 3y would be the most common. And negative 10 could be 5 and 2. Okay, one negative and one positive, since it's a negative. We need to come out to where this adds up to 7y. Whatever these two things, whatever those two products give us. So if we do a 2 and a 5, we could do 4 times 2 is 8, and 3 times 5 is 15. So they give us 8 and 15. What if this was a negative 8 and a positive 15? Well, that adds up to 7y. And so our factorization will be 4y plus 5 times 3y minus 2. If you're not okay with that, that's fine. That one's if we don't, and this is where using a pencil helps, because if we don't get it right, we'll have to erase and start over, or if you're using pen like I am, write a second one over here. Anyway, that's an alternative. I don't know if it's a great alternative for a lot of people, but it's one way that we can move forward and factor this expression. Okay. Let's look at another example. I mean, we didn't really look at anything like this, but I wanted to introduce this concept today, not on Monday. Let's say we have x squared minus 81. Now, technically, there is no number in the middle, so we can imagine that that's basically a 0. Since there's no x power, or no x term in this polynomial, we can imagine that it's going to be in a 0x. So we would need two numbers that multiply to negative 81, but add to 0. Okay. Now, knowing that they add up to 0 means they must be the same number, but opposite signs. So what numbers would that be in this case? Negative 9 and 9. So we have x minus 9 and x plus 9. Right. Okay. Now, let's do one or two more of these, and then we'll see if we can establish a pattern. If we have x squared minus 36, that means we need two numbers that multiply to negative 36 and add up to 0 again. What would that be? Again, if it adds up to 0, we know that it's probably the same number, just opposite signs. Negative 6 and 6. Good? Okay. And so what we see from both of those problems is if we're missing the middle term, then the way that we're going to end up factoring it, the 9 here is basically the square root of 81. You know, because 81 is a perfect square, it's 9 times 9. 36 is a perfect square, it's 6 times 6. And so we're going to end up with plus 9 in one factor and minus 9 in the other factor. Minus 6 in one factor and plus 6 in the other factor. And that's ultimately what happens. This is actually something we call a special product, and we call it a difference of squares because it's two numbers that are perfect squares that are subtracted from each other. Difference meaning subtraction. So we have x squared and we have 9 squared, so the factorization is always x minus a 9, x plus a 9. You know, minus the root and then plus the root of whatever that number is. Same thing here. Square root of 36 is 6, so x minus 6 and x plus 6. Okay? Okay. So, what is our factorization here? If we have x squared minus 9. Yeah, right. We know the factors are going to be negative 3 and 3, so we can get x minus 3 and x plus 3. Good. Well, I could probably use this space over here. What if we have, that's another example, what if we have x squared plus another square, 16? Can we think of two numbers that multiply to a positive 16 and add up to 0? You might be tempted to say 4 and negative 4, but the problem is they multiply to a negative 16 and not positive 16. And then you might be tempted to say positive 4 and positive 4, which multiply to 16, but they add up to 8, not 0. And a similar issue arises with negative 4 and negative 4. So they can't be the same signs, but at the same time they can't be different signs. What does that tell us? Yeah, it tells us there isn't a solution. It cannot be factored. It turns out not everything is factorable, and this is just one instance of that. Okay, this is what we call the sum of two squares, because we have two square numbers being added together, or square terms, I should say, being added together. If the numbers are, or if the terms are subtracted, we can factor it, because we can get the opposite signs, and that actually works out for us. We can't do that with a positive number here, because if the signs are opposite so that they add to 0, the problem is that they don't multiply to give us the positive number. Yeah, so these are not factorable. So if we have a difference of squares, this is x squared minus a squared. We know that it'll be x minus a times x plus a. Okay. And if we have a sum of squares, such as x squared plus a squared, we know this is not factorable. Okay. Now, there are other special products that we have. That is the sum and difference of cubes. Now, these are more difficult. Let's look at the sum of cubes first. For example, you have x to the third plus 27. The first thing in this case, I think it's a little bit more important than in the case with the squares, is to identify exactly what is being raised to the third power. Now, 27 is 3 to the third power, because 3 times 3 times 3, it means we get 9 times 3 is 27. Okay. If we have a sum of cubes, we do have a formula. And the way I like to teach it is based on patterns. Okay. Now our formula, if we have x cubed plus a cubed, is x plus a times x squared minus ax plus a squared. Now the reason this works, or the way I like to demonstrate this, is that since we have x cubed plus a cubed, our binomial is just the same terms, x plus a, leaving off the threes, the cubes. So this is just x plus a. For this term, we remember that x times whatever is here is going to equal x cubed. So this is always going to be x squared. A times whatever is here is going to equal a cubed. This will always be a squared. So basically we square each of these two terms, x squared and a squared, that's here and here. And in between, we multiply these two things together, x times a, or ax, and change the sign. So if this is positive, this will be negative. Okay. Okay. So if we have x cubed plus 3 cubed, what's our binomial, first of all? Remember, our binomial is always the same terms that we started with, but without the cubes. So x plus 3, right? Now we know there's 3 terms in this trinomial. What should come first? So we square this term, so x squared. Okay. What should go last? Three squared will be last, so we could write 3 squared, or we can go ahead and calculate it, which is 9. It works either way. I always think that's the straightforward part. I mean, 4 out of the 5 numbers are pretty straightforward. For the first binomial, take off the cubes, so it's just x plus 3. Square the first term, x squared. Square the last term, positive 9. The one in between, though, is the one that's a little bit tricky. So we multiply these 2 terms together and change their sign. It's not a tricky calculation, but it's sometimes a little more difficult to remember that step versus the others. Minus 3x, good. Now, one thing you may be wondering, can we factor this expression? And the answer is no. For one thing, we can actually check, is there 2 numbers that multiply to give us 9 and add up to negative 3? And the only thing that multiplies to 9, we either have 1 times 9 or 3 times 3, but 1 plus 9 adds up to 10, and 3 plus 3 adds up to 6, neither of which make this 3 in the middle. Which part, Mary? I'm sorry? The 3x here? Okay. The way that we get minus 3x is we take the x times the 3, which is x times 3, or 3x, and then we change the sign from whatever was here. If this one's positive, this is negative. So again, we drop the exponent, so it's x plus 3. Square the x squared. Square the 3, 9. And then we multiply them together and change the sign, so minus 3x is the last part. Now the way this happens is, as long as the original problem did not have any common factors, which it doesn't, then this expression will never be factorable. And that's true for either the sum of cubes or the difference of cubes that we'll look at next. Okay. So, looking at another example, we have x cubed minus 64. Again, step one is trying to figure out what exactly is being raised to the third power to equal our number. So does anyone happen to know what number raised to the third power is equal to 64? It's 4 cubed. Good. 4 times 4 is 16, and times 4 again makes 64. Now, if we learn our pattern from the other problem correctly, this actually has the exact same pattern. Even though it's subtracted, the pattern is exactly the same. In the parentheses here, we drop the cubes. It'll just be x minus 4. What would come first in the trinomial? X squared. You always square this term, so x squared. What is last? Four squared. Yeah, square this number. So that would be a, whether it's positive or negative, when we square it, it does become a positive 16. And again, the middle number, multiply these two terms together and change the sign. So what would we have in the middle here? It would be plus 4x, correct. Now, this is not the easiest thing, but personally, and again, this is me, you may find it easier just to think of it as a formula. I like learning the pattern, that way I can reproduce it whenever I need to. And that's definitely what I would recommend. If we could recognize the pattern that's created and remember the pattern that's created, it helps us recreate that anytime we need to. Technically, a formula does the same thing, except I find that it's easier to memorize a pattern than a formula. Maybe just me, I'm not sure actually. But as always, whatever you find will make you the most successful, I recommend you follow that way. But so our pattern works regardless of whether it's a sum or difference of cubes. So we did it here with minus 64, and we did it in the previous example with plus 27. Let's see, there you go. But the pattern is the same in both cases. And again, trinomial is not factorable, so this is all that we have to do. Now, overall, we're not going to be factoring sums or difference of cubes all the time. It's actually much more likely that we see a difference of squares like we had looked at already, rather than looking at one of these. So, very occasionally we need to do this, and if we have to look it up sometimes, that's fine. But most times we're not going to be in a position where we have to memorize exactly how to do that. So. But I wanted to go through the process at least and demonstrate that Now the book throws out some weirder numbers. Let me show you 68 on page, still on page 24. (216y to the third) minus 343. Now, probably you don't recognize 216 as 343, and you don't recognize either one of those as being perfect cubes, but it turns out they are. Like I said, it's okay if you don't recognize it. 216 is 6 to the third, and 343 is 7 to the third. That's actually part of the struggle in this problem, is figuring out exactly what has been raised to the third power to equal 216. And one way that we can achieve that on our calculator is a lot of calculators will have a cube root function built in. In my case, it's above the x cube button, so if it's cube root of x, that's second cube root, and enter 216, and it gives me the value of 6, so that is 6 to the third. That's another way we can use our calculators to help us figure out these things, especially if it's one that we're not familiar with. Probably most of you know that 1 cubed is 1, 2 cubed is 8, and 3 cubed is 27. After that, it might get a little fuzzy, which is okay. I actually memorized all the cubes up to 12 in high school, because I was part of this UIL competition. But that's just me. I don't expect everyone to do that. But I certainly have a higher ability to recognize these things, I guess, because of that. Anyway. Also, years of practice, it turns out, is very helpful. Anyway, so once we figure out exactly what these numbers are cubed, the pattern is still the same. It's a little bit more complicated because we're not just working with plain y cubed. We have 6 cubed y cubed. But the pattern is the same. What is our binomial, first of all? Six y minus 7. Again, just leave off the cubes, so 6y minus 7. Okay. First term in the parentheses. Now, let's be careful about that. We know that we're going to square the 6y, but when we square 6y, we square both the 6 and the y. So 36y squared. Okay. What about the last number here? Plus 49, good. Yeah, 7 squared is 49. What about in the middle, based on these two terms? not 7. 7's part of it, but not all of it, it turns out. Remember, we multiply these together. And it is positive. $42, right. Yeah, because we have to do 6y times 7, which means we multiply the numbers. In this case, 6 times 7 is 42. We also have the y, and then this is a minus, so we change it to a plus 42y. And that's part of why I stressed that we actually multiply these two terms together. It's simple enough when it's not simple, but anyway, it's slightly easier, I guess, when we don't have a number in front here, so it's just x times 4, we know it's 4x, and we make it plus. But with the 6y and the 7, we still multiply the numbers together, and we have our y, and we change our sign. Okay. Okay. Now, this is not in the book, but I wanted to show this example. What if we have x to the 4 minus 16? Well, it turns out we don't really have a formula, per se. Yes, we could make one if we wanted to, but we don't really have a formula that we teach for what would be considered a difference of fourth powers, or what we call it, quartics. That doesn't. Let's do a difference of fourths. So we know 16 is 2 to the 4th, and we have x to the 4th also. But we don't really have any pattern for when they're fourth powers. We do have a pattern, though, for when they're squares. And even though these are both fourth powers, they're also both squares. Okay? Because we know 16 not only is 2 to the 4th, we also know it's 4 squared. Okay? Now, what squared is x to the 4th? How can we write that as expression squared? Does anyone happen to know that one? This is one I don't think I taught, but you might figure it out. I have confidence in you. X squared, yeah. Now, let's make sure we understand this step. The way that we take a square root of a term with an exponent, like this, a variable with an exponent x to the 4th, is we actually factor this number into something times 2. In this case, it's 2 times 2. But what happens is, if we're trying to take this expression and go backwards to the original, if we have x raised to a number and then raised to another number, we actually multiply those two numbers together to get back to here. So if this had been a 6, it would be 3 times 2. But since it's a 4, we know it's 2 times 2. I want to stress that it's multiplying these two numbers rather than adding, because in this case, It's actually true either way. We could take 2 plus 2 and equal 4, just like 2 times 2 is equal to 4. But the rule is actually based on the multiplication of those two numbers. That's why I wanted to stress that. This should actually be 2 times 2 to get back to the 4. So it's like we're dividing it. 4 into 2 times 2. Okay. So what we have now is a difference of squares. And we know with our difference of squares, we can write x squared minus 4 and x squared plus 4. Okay? Because whatever's being squared, it's repeated here and here, and then whatever's being squared is repeated here and here. And we know for a difference of squares, we have to have opposite signs. Can we factor x squared plus 4? No. Yeah, with the plus, we know it's not factorable. This one, however, this one is still a difference of squares. So we know we can take that one step further. It's just that the x squared plus 4 will have to stay the same. We won't be able to break that down any more than it already is. So if we have x squared minus 4, what are the other two factors that we create based on that? X plus 2 and x minus 2. Okay. All right. Any questions on these before I move on? So I want to move forward to section 1.7. I think we'll get started on it today, but may not finish it. We'll at least get started though. Okay, section 1.7 is on quadratic equations. Specifically, we're looking at solving quadratic equations. So, we're going to look at 3 primary methods for solving. One is factoring, to go along with what we just discussed in section 1.4. Second, we have the square root property. And third, we have the quadratic formula. Okay. So we're just going to look at the factoring element today, since that really goes along well with what we had just talked about in section 1.3, which is all about factoring. And the idea is that to be able to factor an expression, we can then use what's called the zero, what do they call it in this book? Zero product rule. Or zero factor property. Fair enough. So this book calls it the zero factor property. And the zero factor property says that if a times b is equal to 0, then a is equal to 0 or b is equal to 0. Okay. So what that's saying is that if we multiply two numbers together and somehow come up with a 0, the only way that's possible that we multiply two numbers and get a 0 is if one of the two numbers is 0 to start with. So either we have 0 times b, which is 0, or we have a times 0, which is 0. Okay, that's the only way to get a product of 0. So if neither of these numbers is equal to 0, then there's no way it equals 0 on the right. Okay. Now, to factor and solve equations, the equation must be in what we call general form, and it must be equal to 0. So what we mean by that is we must have ax squared plus bx plus c equal to 0. So that means everything on the left-hand side is just a normal trinomial. Put the highest exponent term first, and then the decreasing order from there, and it's equal to 0 on the right. So if it does start off where it's not equal to 0, like we have a constant over here, well, our first step will always be make it equal to 0 by subtracting that number, and do that from both sides. Okay. That's our zero factor property. Let's look at applying it. So now we're on page 58. This will be number 2. Now in this problem, they've already factored it for us. We have p minus 10 times, actually no, that's a 16, my bad, times p minus 5 equal to 0. And the idea is, with the zero factor property, we know this product is equal to 0, so either the first thing is 0, because we have 0 times this would be 0, or the second thing is 0. So we would say p minus 16 could equal 0, or p minus 5 could equal 0. And the question is, how would we solve this equation for p? Well, if we want to get the variable p by itself, then we have to do the opposite of the number there, which in this case we have 16. So the opposite of a negative 16 would be to add 16 to both sides. Okay. Same thing happens here. If we have p minus 5, then we add 5 to both sides. So p is equal to positive 5. And right there is our two solutions. What would make this a little bit more complicated is, if we actually start off with a trinomial to factor. For instance, this is not an example, it's a specific problem. Let's see, number 4, we have x squared minus 2x equal to 0. Now in this problem, it's not a full trinomial because we don't have a constant. But do we have a common factor in this problem? Do we have a greatest common factor that we would be able to factor out from each part? One, it doesn't matter which one goes first, so the order is not important. Yeah, we have to be careful because this 2 is the exponent, so it's not something we would consider factoring out. But both of these, if you remember, that's x to the 1. That's alright. We're still learning. It is important to practice this so we can get better. Both of these have at least an x. Okay? So our GCF is x. This one has 2, x squared, and this is 1, x to the first. So 1x, or just plain x, is our greatest common factor. So we want to divide each of those by x. So x squared divided by x to the first, we subtract 2 minus 1, which gives us x to the first, or x. 2x divided by x, the x's basically cancel out of that, so it's just a 2. Okay. Now again, according to our zero factor property, we set each part equal to 0. And solve for x. Technically, we already have x here. X is equal to 0. In this case, we'll need to add the 2 over. So we get x is equal to 2. Now, looking at these two problems, at least number 2, you probably recognize that there's a shortcut that we can take to go from here directly to here. Now, if we're not sure, I encourage you to set each part equal to 0 and then solve them accordingly. But really what's happening is we're just taking the opposite of whatever number is here. If we have p minus 16 as our factor, so positive 16 will be our solution. We have x minus 2 as our factor, so positive 2 will be our solution. Okay? Number 6, we have x squared minus 64 equal to 0. How do we factor x squared minus 64? Well, we need two numbers that multiply to negative 64 and add to 0. Because again, we don't have any number between these two, and no term between those two that would normally be there. X plus 8 and x minus 8. And again, this is our difference of squares, so we can certainly use that as well, or instead of this approach. Because we know x squared is x times x, 64 is 8 times 8, and in order to get a negative, we have to have 1 plus and 1 minus. So then, now that we still have an equation to solve, we said x plus 8 equal to 0, and x minus 8 equal to 0. This is a 0. On this side we'll subtract 8, so x equals negative 8, and this one will add the 8 to both sides, so x is equal to 8. That's really only one or two additional steps to what we did in even factoring them in the first place. The more complicated part is still probably factoring than actually finding the two zeros or the two solutions. Because that's just adding or subtracting, it turns out. Okay. Let me do one more example. In this example, we have x times x plus 4 equal to 12. Now again, we remember that we needed the expression to be in a specific format, which is ax squared plus bx plus c equal to 0. That means we can't have these two things multiplied together still, so we'll have to do that multiplication. And because we have a 12 on the right hand side, we're going to have to subtract it over to the left. That way it'll equal 0 on the right. Now we'll go ahead and distribute these first. X times x is x squared, and x times 4 is a positive 4x. Then we'll subtract the 12 over. So we have x squared plus 4x minus 12 is equal to 0. Notice that the 12, even though I kind of wrote it underneath the 4x, there really wasn't any constants on this side, so it's really separate from everything else. These are not like terms, nor are these, nor are these. Okay, we have to be very careful. We only combine like terms where they have the same variable. So we can combine x squares together, we can combine x's together, constants together, but not between each other, just individually. Alright, and now we need two numbers that multiply to negative 12 and add to positive 4. Six and negative 2. So we'll do x plus 6, x minus 2 as our factors. And again, we know we could set each of these equal to 0. X plus 6 equals 0. And x minus 2 equals 0. Here we subtract the 6. So x equals negative 6. And this one we add the 2 over. So x is equal to 2. Okay. Any questions on these? When we were learning to factor these, we're basically 3/4 of the way there. We still have to figure out what x is actually equal to, so we then set each of our factors equal to 0 once we're done factoring, and then solve it for x from there. Okay. Alright, let me pick out some homework problems real quick. Again, just wanting you all to practice these. On page 24. Look at 49 and 55. 63 and 67. And then on page 58, get 1 through 9 odd. Okay. Yes, if you've worked it out already, you can email that to me. And again, the homework from Monday is due next Monday. This homework from today is due Wednesday. What is that? The 28th. That's it is. Okay. Hopefully, everyone has access to the ebook at least, or they have a physical copy of the textbook. So you can go into your ebook in MyMathLab for your other course and look up these page numbers and just work them on your own paper from there. And send me pictures or scans of those pages. That should be sufficient for submitting your work. Anyway, I wish we could do MyMathLab for both classes simultaneously, but apparently it's not an option. Anyway, go ahead and look at these, like I said. And certainly email me if you have any questions or if you're having any issues with the technology side of things where you're trying to send me your work but you're having trouble. Let me know and I can see what I can do to help you out. Otherwise, have a good weekend, and we'll continue in section 7 on Monday. Okay? So you all take care, and I'll see you then. Bye.